Hi all. In a previous video, we had learnt about principal component analysis, which is a very popular method for dimensionality reduction in machine learning. So there, as you might know by now, that we essentially use the concept of eigenvalues and eigenvectors to do dimensionality reduction. So in the previous video, I had introduced you to this concept from an intuitive perspective. Now in this video, I am going to explain the same idea using mathematical derivation so that you can see why is it that eigenvalues and eigenvectors are playing a role. So essentially what we are going to learn is this concept of principal component analysis. So let's say you have capital N number of data points and each data point is xn, where n goes from 1, 2, 3 up to n, and each xn is a column vector of d length. So by length I mean the number of rows in the column vector is equal to capital D, and that is our dimensionality. So here please don't get confused between the notation of the previous video and this one. In the previous video, x1 and x2 were two different features or two different dimensions of your problem. Here we are using xn, the subscript n, to denote different data points. So here x1, x2, x3, x4, x5 and so on are different data points, and each of these x1, x2, x3 is a d-dimensional column vector, and our objective is to project this to m dimensions, where usually m is not just smaller but actually much smaller than capital D. So now for the sake of simplicity, let's take m to be 1. So we can generalize that to the case of m equal to 2, 3, 4 and so on. But to make the math a little simpler, let's take m equal to 1. So what is our objective? We have a d-dimensional data set and we want to find a linear combination of these different dimensions so that we can choose one single linear combination of all of these dimensions, which gives us the best possible accuracy when we do classification using some appropriate supervised learning algorithm. So let that direction that we want to find be denoted by u1. So here u1 is also a column vector of dimension d. So u1 and x1, x2, x4 and so on, they all have the same length, capital D. So now when we project our given data points xn along the direction u1, we will be left with a projected data point which has only one dimension. So that is represented by yn. So the projected data points are yn, which is nothing but u1 transpose times xn. So here u1 is a d-dimensional column vector, xn is also a d-dimensional column vector. So u1 transpose becomes a row vector. This is a column vector, so when you multiply you get a scalar. Similarly you do for all the different n's, so you will correspondingly get the projected data points, which now are just a scalar. So this is because we have chosen m equal to 1. When you take m equal to 2, for example, you will get two directions, u1 and u2, each of which will be d-dimensional column vectors, and then using that you can get two-dimensional projected data points. So this is our projected data point, and the mean of this projected data points, which is denoted by y bar, this is nothing but u1 transpose into x bar, where what is x bar? X bar is the sum of all these xn's divided by capital N. So now since our projected data points yn are just a scalar, so we can find the variance using our standard formula. So the variance of projected data points is given as Sy is equal to 1 by capital N summation over all n u1 transpose xn minus u1 transpose x bar whole square. So this is just the standard formula for the variance of a scalar, and there is nothing different that we are doing. So now this square quantity can be written using matrix notation. So you get 1 by n summation over n u1 transpose xn minus u1 transpose x bar multiplied by u1 transpose xn minus u1 transpose x bar transpose. And now what we can do is that we can take this transpose inside over here. So then this multiplication will flip. So then what do we get? We get 1 by capital N summation over n u1 transpose xn minus u1 transpose x bar into xn transpose u1 minus x bar transpose u1. So now what we can do is that we can take u1 transpose outside of this bracket, and we can take u1 outside of this bracket to the right. So then this becomes 1 by capital N summation over small n u1 transpose into xn minus x bar into xn minus x bar transpose into u1. And now because our u1 transpose and u1 do not depend on small n, so we can take this outside of the summation and we can write this as u1 transpose sx times u1, where your sx is equal to 1 by capital N summation over n xn minus x bar into xn minus x bar transpose. And this is the covariance matrix of your Sx. So using the covariance matrix of your Sx and using your knowledge of u1, you can compute the variance Sy. So now what is our objective? Our objective, if you remember the earlier video where we discussed about the PCA algorithm from an intuitive perspective, is that you want to find that direction of projection such that the variance of all the data points is maximized, meaning that the spread of the data points along that projected direction is the maximum. So what we want to do is that we want to find u1 such that when we do this multiplication, Sy is maximized. However, we also want to keep the magnitude of u1 fixed, because if you take u1 to be very, very large magnitude, then this number is also going to go up. So keeping the magnitude of u1 fixed to unity, we want to maximize our Sy. So now our objective is to maximize Sy keeping u1 norm. So this represents norm, which is the length of the vector, fixed. So we are again going to use the concept of Lagrange multipliers, which we had used while discussing SVM. So if you are not familiar, please go back and take a look at the Lagrange multiplier problem. So if we define this function L equal to U1 transpose Sx U1 plus lambda 1 times 1 minus U1 transpose U1. So now this lambda is our Lagrange multiplier. So now our objective is to maximize capital L by changing U1. So let's do that. So how do you maximize? You take a gradient and equate that to 0. So you take a gradient of L with respect to U1 and you equate that to 0. So when you take this gradient with respect to U1, what you get is Sx times U1 is equal to lambda 1 times U1. So now if you remember, this is clearly the eigenvector eigenvalue kind of equation. So here our U1 represents the eigenvector of Sx and lambda 1 represents the eigenvalue of Sx. And what is our variance in y? So Sy was equal to U1 transpose Sx times U1. Now we have found that Sx times U1 is lambda 1 times U1, and because we have kept the magnitude of U1 equal to 1, so this is our equal to lambda 1. So now if you choose a particular direction U1, the variance along that direction will be exactly equal to the eigenvalue of the corresponding eigenvector. So now if your Sx is some d cross d dimensional matrix, you will get d number of eigenvectors and d number of eigenvalues. And now you need to arrange these eigenvalues in a descending order and pick a few from the top, so that the corresponding eigenvectors are the ones in which direction the spread of your data points is the maximum. So essentially, in order to maximize your Sy, what you do is that you choose the eigenvectors corresponding to larger eigenvalues. So now using this procedure, we have identified one eigenvector and one eigenvalue, but now you can clearly see that the same procedure can be easily extended to any number of eigenvalues and eigenvectors. Basically, if you take your capital M to be, let's say, 3, then you arrange your eigenvalues in the descending order and pick the top 3 eigenvalues and the corresponding eigenvectors. So this process, although we have done for the simple case of one eigenvector, but it can be very easily generalized to any choice of capital M. Now you may ask, what happens when capital M is equal to capital D? Do we get back the exact same input data points? The answer is no. When capital M is equal to capital D, then the new eigenvectors that you get are just rotations of the existing coordinates, and so you still get a better representation than what you have to begin with. So even if you do not want to do dimensionality reduction, but even then your PCA will definitely make your supervised learning classification accuracy better by some extent. So now, as you can see, we need to compute the eigenvectors and eigenvalues of the matrix Sx, which is a d cross d dimensional matrix. Now there are some problems, especially in the domain of deep learning, where the number of features is much larger than the number of input data points. So essentially, you may be in a regime where your capital D is much larger than capital N. Now why is that a problem? Now, as I said, this can happen when you have a small data set of images, because images in general are very high dimensional data. And so what happens is that finding the eigenvalues and eigenvectors of Sx, which is a D cross D dimensional matrix, requires computations of the order of D cube. So if your D is very, very large, then the number of computations required to find the eigenvalues and eigenvectors will be very, very large. So now there is a way to solve this problem, that instead of doing D3 computations, you can actually do N cube computations. So in order to see how that is done, let us define a new matrix. So now let us define a new matrix, capital X, which is a capital N cross capital D dimensional matrix whose nth row is given by xn minus x bar transpose. So xn, as you know, is a D dimensional column vector, and when you subtract that by x bar in order to make it centered around 0, and then if you take a transpose, it becomes a row of size D, and that is your nth row. So you have row 1, row 2, row 3 and so on up to row capital N, corresponding to the total number of data points. So now your covariance matrix Sx is simply written by 1 by capital N, capital X transpose capital X. I would like you to verify that this is indeed the same formula for Sx that we wrote some time back. So now what is our objective? Our objective was to solve this equation Sx times ui is equal to lambda I times ui, where ui is the eigenvector and lambda I is the eigenvalue for the matrix Sx. So what is Sx? It is 1 by capital N, capital X transpose, capital X, ui is equal to lambda I times ui. Now if we multiply both sides of this equation by capital X, what we get is 1 by capital N, capital X transpose, capital X ui is equal to lambda I times capital X times ui. So now we can write this as a new vector. Let's write that as vi. So what we will get is 1 by capital N, capital X transpose, vi is equal to lambda I times vi. Now notice that this matrix is a n cross n matrix, because your capital X is n cross d, capital X transpose would be d cross n, so d cross out, what remains is a n cross n matrix. So now the problem we had with this equation was that this is a d cross d matrix, and because our d is very large, computing this would require order of d cube number of computations. But now this is a n cross n matrix, so solving this would require only capital N cube number of computations. And because for this particular problem our capital N is much smaller than capital D, so this helps us in reducing our computational cost by a very large extent. And the nice thing is that this matrix has the exact same eigenvalues as this matrix. So we find the corresponding eigenvalues for this matrix and arrange them in descending order and pick the few top ones that will give us the exact same results as what we would have got by solving this equation. So this is the real power of PCA, that by using a very simple technique which is taught even at the school level, we can do dimensionality reduction of very complex problems, and that helps us in significantly reducing the complexity of supervised learning algorithms. Now, as I mentioned earlier, that one limitation of this PCA algorithm that we have discussed is that it does only linear combinations of the input variables. Now, that does work well in most cases, but there could be some examples where you may need to do nonlinear transformations. So there are some kernel tricks which I'm not going to get into right now, but there are some kernel tricks that you could use for solving those problems. So I strongly recommend you to implement PCA by using the Python code given in the description box, so that your understanding of this concept can become much better.